Hi students, so today we start lecture 64 and today I'm going to talk about ballistic entry. So essentially if we have any spacecraft which is entering the earth or any other planet, then this is the equation we are going to derive today. We are also going to discuss about something known as the exponential atmosphere which is used in the ballistic entry derivation. This is lecture 64. I am Dr. Ranjan Ganguly. Now, we have discussed some of the things about how to orbit the Earth, how to escape it, and so on. We have talked about circular velocity and escape velocity. We also talked about satellites. So now we need to do something which is return back to Earth. And whenever you are returning back to the Earth, or if you go to some different planet, you may be entering into that planet. Then essentially this is known as the entry problem or the re-entry problem in case you are using a vehicle like a shuttle which is going up and going down. Now, one of the things which happens with such a vehicle is that you may often fly at very high speed. So your Mach number may be in the range of 30 or even more. So these are essentially all in the hypersonic speed regime. Now, when you are flying at such a high speed and you want to come back to Earth, the atmosphere being what it is, you are going to have two main problems. One is that you are going to go through a major deceleration of the spacecraft, and essentially the speed is going to reduce dramatically in a very short period of time, and this is going to create a lot of problems for anybody who is in the spacecraft. The second problem you are going to get is high temperature problems, and this is because when you enter the atmosphere there is a rise in temperature on the entire surface. Remember, this vehicle is made of some kind of material. It could be metal, it could be ceramic composite, it could be something else, but what's going to happen is that it's going to take a lot of drag, and so this is going to lead to high temperature. So these are some of the effects which are going to take place for the re-entry vehicle or the entry vehicle to the earth. Now let's look at some ways in which you can enter the earth. So one of the approaches is known as ballistic entry, and here what happens is that your spacecraft is here and you simply come down like this. Here there is no pilot control, you just use drag and gravity to fall onto the earth, and this is the situation which was often used in some of the older spacecraft and even in some current spacecraft. Essentially you fall into the earth, and very near the earth you may use some kind of parachute to actually land in the water, or you may land somewhere on land. So generally water landing is preferred in many cases. Now the second case can happen if you do an entry which is divided into two basic parts. So essentially you come down, and as soon as you enter the atmosphere you try to glide down to some location on the earth where you can do a landing similar to an airplane. So what happens in this kind of situation is that the first part of this landing, remember there is no air out here in the far reaches of the atmosphere or beyond this blue line which I have drawn. So in this region you can fall pretty rapidly, but as soon as you enter the atmosphere you glide, you essentially reduce this angle to a lower angle, and so you are able to fly somewhat like an airplane. So in this case what you would need is you would need a lift to drag ratio which is reasonably high. You would need some kind of wings on this vehicle. So this vehicle then is no longer a pure rocket, it is some kind of vehicle which is between an airplane and a rocket. It has to have both these functions. Now, this airplane or shuttle essentially flies to the earth like an airplane. One of the advantages of this kind of vehicle is that it is reusable. So, in many cases, we do not want to simply lose the vehicle into the sea or let it go completely in the atmosphere by burning. So, we can use some kind of space shuttle or reusable vehicle like this. So just to summarize what we learned till now, we see that one of the things which happens when you enter the earth rapidly is that you have a high level of deceleration. Now, deceleration should be kept at less than 10 g because there are people in the vehicle, and so if you are doing anything which is manned, that's a constraint you need to consider. Now, in cases where heating develops, what will happen is that you must ensure that as far as manned flight is concerned, there is tolerable temperature for the people when you are landing. And in case you are using some kind of unmanned system, at least it should not burn up. And also the different equipment which are present in the spacecraft should also not be deleteriously impacted. Now let's look at the possible corridor which you have when you are entering back into the earth. So in many cases you may enter the earth through the parabolic or hyperbolic trajectory, and in this case two kind of situations can happen. One of them is shown in this path here. So what can happen here is that the deceleration rate is too high, and so you simply crash into the earth. So this is not something you want, because you will be exposed to all those high G problems, high temperature problems, and so on. The second possibility is that the drag is too low, and then what happens is that this vehicle has escaped the atmosphere of the earth and it goes on somewhere out there in space. So both these scenarios are not good. What you want is in this green corridor which I have made, which is known as the entry corridor. So here what happens is that there is a particular path of approach which is somewhere between this region of high deceleration and this region of drag being too low, and you need to fly in within this corridor if you are coming to the earth. So the boundaries of this corridor are known as the undershoot boundary and the overshoot boundary. Now let's take a look back at the standard atmosphere, and we are going to do that because we are going to derive something known as the exponential atmosphere. Now when we started this lecture series, we had taken a look at the standard atmosphere, which is essentially a definition in terms of the temperature. So this line graph which is shown here, it's a set of lines which are out there. Some of them are in this manner, some of them are in this manner. So these are known as the isotherms here, where temperature is constant. So what happens here is that when you start at sea level, your temperature is 288.16 Kelvin, then it decreases to 16.66 Kelvin, then it stays constant, then it once again changes to 282.66 Kelvin, and so on. Now, of course, you know that temperature is a function of height, and that is what this plot essentially tells you, that temperature on the x-axis in Kelvin is a function of the height which I have given in kilometers. Now, interestingly, most airplanes fly within the range of 18 to 13 kilometers, and these are the planes which are typically used for passenger jet transports. These are the planes which fly quite high up. Remember from our previous class discussions, there is a reason why jet planes fly high up, because that's where the range becomes better. Now, even if you take this 10 to 13 kilometer, it will be somewhere in this region, because here you are going from 11 kilometer to 25 kilometer, and this is the region from 0 to 11 kilometer. So most of the time you are flying in this region, and you do not most of the time encounter this kind of regime in a typical aircraft, but in a spacecraft you are going to encounter that, because you need to get out of this entire regime, and if you are falling back, you need to fall back through this entire regime here. So let us look at the equations we have seen before also. So we know that temperature is a function of height, pressure is a function of height, and density is a function of height. So also I know the hydrostatic equation which we derived a long time ago, that is dP is minus rho g0 dH, and we know the equation of state, which is P is rho RT. Now what I can do, I can divide these two equations. So I get dP by P is minus rho G0 dH by rho RT, which gives me minus G0 by RT into dH. Now I can immediately write this formula here. This formula is going to be very important for me, because I am going to now get the relationship between pressure and H, and then I am going to get the relationship between density and H, which is going to give me the exponential atmosphere. So let us first get the relationship between pressure and height. So pressure is a function of height. So I had this equation in the previous slide. Now what I do is I integrate this, and I will assume that there is an isothermal layer, in which case I can go from P1 to P and H1 to H. So the one subscript is the bottom part of this layer, and the subscript which has, or rather the no subscript case, is the general location in this layer. So I perform the integration. So I know 1 by p will be log. So I get log p by p1. Now this is the natural log to the base e, and then I get the right hand side here. I simplify this to p by p1 is e to the power minus g0 by rt h minus h1. So this is a exponential variation. So now I'm going to take this and I'm going to try to get the density expression in the next slide. So let's look at the density. Now to get the density, I use the equations of state at 2 points. So at the point 1 and at the general point, I will have these two equations here and here. And again, I divide row by row 1 in these two equations. So I get P by RT by P1 by RT1. And this gives me P by P1. Now I can immediately write the equation here, which I have given in yellow. That is the density ratio. And now I already know P by P1 was this equation from the previous slide. So I can put this back in here. And I get row by row 1 is this equation here. Now remember, I could cancel T and T1 because I was considering this to be an isothermal layer. So here T1 is equal to T because the temperature is the same. So this particular equation is going to give me the exponential atmosphere. So let me assume that H1 is sea level, and if I do that, then I can simply remove H1 here because H1 will become 0, and so I get this equation here. Rho at that value is 0 also. So for H1 I put 0, for rho 1 I put rho 0. Now this particular equation here is known as the exponential atmosphere, and it is often used in the equations we are going to derive today, and it's going to make things simpler for us in the case we want to formulate that equation. So that's something which we want to do here. So this equation here generally is correct to about 140 kilometers, which is quite a long distance from the Earth, and this agrees with the Earth standard atmosphere in this region. Now I take this equation here and I can write this coefficient g0 by rt as some variable z, and then I write this equation here. So I get e to the power minus zh or minus zh depending on your particular predilection. So this equation is something which is going to be very important for us. So remember this, this is the exponential atmosphere, that rho by rho 0 is e to the power minus ch, z being g0 by rt. Now let's look at the spacecraft, and what we are going to do is we are going to try to derive the equations of motion for the spacecraft. So here what we have is we have the Earth here given in green. So we have the center of the Earth somewhere here, and the spacecraft is flying here. Now the spacecraft is at a distance rc from the center of the Earth, and the altitude with respect to the sea level is h. Now the spacecraft is subject to lift, drag and weight. There's no thrust there. We assume the thrust is 0 because we are trying to get back to Earth, and the spacecraft has a certain velocity given by v. So as usual in the fluid mechanics we discussed before, the lift is normal to v and the drag is parallel to v, and w is in the direction of the Earth. So it acts along this particular line. Now I can immediately get two equations here. One equation in this direction I will get as minus d plus w sine theta equals m dv by dt. So remember this angle is theta here, so I can take this angle to be theta, and so w sine theta is in this direction. Now the second equation I get is L minus W cos theta, which is in this direction, is m v square by rc. So that is the force acting toward the center of the Earth. So we are going to be dealing with this equation in yellow today. That's the main equation we have to keep in mind. So let's start with this equation here, and now I'm going to do a change in variable. So we are going to take this coordinate s, which is along the flight path. So this is the distance, and then we can write m dv by dt as m dv by ds into ds by dt, that is m into v into dv by ds. So this is nothing but the chain rule from calculus, and we use the fact that ds by dt is v. That's basic definition of velocity in terms of distance and time. So I get half m dv square by ds. That's the equation here. Now what I can do is I can use this equation in this equation here. Now before that we'll make one more transformation. We will use the fact that dH is minus ds sine theta, and that simply comes from the geometry of the problem and the fact that theta is actually now negative with respect to the horizontal line. So it's measured with respect to the horizontal line that's positive in that direction. So that's why the change in sign happens here. Now the basic definition of drag is d is half rho v square s cd, cd being the drag coefficient, s being the area we are using here for the reference. And then we can write this equation out. So what I did, I put d here, this value, I have the w here, of course, I then have also this value here, and this is coming from dv by dt, which has been substituted here, m dv by dt as this term, and also I have substituted ds is dh by sine theta, so I get dh by sine theta, and that is a negative sign which comes because of this definition we have linking dh and ds. Now I'm going to just write this equation, and now I'm going to bring in the exponential atmosphere into this problem. So remember, exponential atmosphere was rho by rho 0 is e to the power minus zh, and so I differentiate this, so I get d rho by rho 0 is e to the power minus ch into minus z dh. So again, this essentially comes by simply differentiating this function here and h being a variable. So now what I can do, I can take this e to the power minus zh and I can replace it by rho 0 from this equation. So I put this here and I get rho 0 minus z dh, and then I get the relationship dh is minus d rho by z into rho. So these rho zeros cancel out and rho and z go down in the denominator, and I get this nice looking equation here. So now I'm going to take this dh and I'm going to plug it into this equation here, which we had for the drag relationship. So we do that, we take this equation and we take this equation and we combine them. So what I have done is I have replaced dh here by d rho by z rho. So I get this equation here. So what happened, d rho came here and the z and rho term went up. Now I take this equation and I divide throughout by this quantity z rho m sine theta, and also I multiply by 2 throughout. So I get this equation here. Now once I get this equation, I can do some cancellation. So I cancel all the terms which are common. So I can see the m is common here, the sine theta is common here, the rho is common here, and so on. And so I get this simple equation here. Just to check here, what would happen here? Only 2g would remain because m sine theta cancels out. And here what remains is z into rho. And similarly, I have a term here. Now what I do is I take this g term to the I keep the g term here and I take this term to the right hand side. So I get this equation which I have put in yellow, and also I move some of these terms in the denominator. So I get this equation here. Now this equation in yellow is a key equation which we are going to consider in detail later, and we see it's nothing but this equation. All we have done is we have replaced some of the variables. So instead of dh, we were able to write things in terms of d rho, and also we have simplified this equation to some extent. So one of the aims of this entire derivation is to get a relationship between this velocity and density. So again, I have just written this equation here, and now we know that this value m by cds is known as the ballistic parameter, and for this equation we can solve for different values of v and vh. So essentially you can see here, but what happens is that it's actually not as simple as it seems, because in general theta is a function of h. So you will also need the first equation involving lift to solve it, and this is given in many books on space mechanics. We are not going to try to solve the general situation because that can be done using numerical methods and so on. Instead, we are going to try to solve a special case and get some physics out of this equation. So let's do that. Let's take this equation, and what we are going to do is set this right hand side involving g to 0. So this term becomes 0 because what I have assumed here is that the drag is much greater than the weight. And remember, the weight term comes from this, the drag term comes at CD here. So I could get rid of the weight term. Now, generally in ballistic entry, the lift would be 0 and the drag would be much greater than weight. I would get this equation here, which I can rewrite in this form, which has become more amenable to closed form solution or exact solution. But there is still a problem. The problem is that we will have to consider theta to be a constant to handle this equation here. So we will assume that, and we will also assume that rho is 0 at V is VE. That is, you are entering the atmosphere. At that point, the density is 0 and your velocity is V subscript E. And when you have entered the atmosphere, your density is rho and your velocity is V. So essentially, this equation can then be integrated now with the boundaries on the definite integral being that at rho 0 you have VE and at rho you have V is V. Now once I integrate this, I would get the ln term here for this, and then I can take the exponential powers on both sides and I get this equation in yellow, which essentially gives me the relationship between V and VE in terms of this exponential function and the ballistic parameter m by CDS. Now, the solutions of these equations are quite complex. We are going to just show the end result, how it may vary. So for example, if I were to look at velocity versus the height and the density here, remember the density is coming down, the altitude is going up. There can be several different paths of this velocity depending on the values of m by CDS or the ballistic parameter. So essentially when you are far out there, there is essentially no drag and you are just coming down like that. Your velocity is more or less constant, and then your velocity starts decreasing and then you finally drop here at some point. So the same thing would happen at a different curve here, and the velocity decrease takes place in the atmospheric region because of the high drag which is present here because of the air being present. Now if m by CDS is high, you can take a trajectory like this. If m by CDS is small, you can take the trajectory shown in the red. So essentially the ballistic parameter controls the kind of trajectory you go through once you enter the atmosphere of the earth. So that's why that parameter is important, and you could control it by manipulating the mass of the spacecraft by looking at the CD value and also the area which you have. So by tailoring that particular value, you can tailor the entry mechanics or the trajectory of the vehicle. So let us summarize some of the main things we learned today. We saw that deceleration and heating are very important as far as atmospheric entry of spacecraft are concerned, because deceleration does impact the people sitting there. It can also impact the equipment and so on. And heating, of course, is negative for the material. It may be negative for the people also. And it may lead to damage to the various equipment and subsystems and so on. The equation we derived today, this equation here, is the equation of motion of the spacecraft as it is coming back to Earth. And this equation is pretty universal. You can use it for different planetary systems also by adjusting the different parameters. Now, one key parameter here was m by CDS, which is the ballistic parameter, which will control the trajectory of its coming down on Earth. Now, the solution of this for a special case where theta was constant and we were ignoring the weight was given by this equation here. So this is something which we can use to get an idea about the velocity versus the entry velocity which the spacecraft sees as it enters the Earth at a constant angle theta. So again, that's something to remember. This is a special case for the equation. If you want to consider the general case, it is given in various books on space mechanics. And in that case, what you would have to do, you would also have to consider the first equation, which we didn't talk about much. That is the equation involving lift. You have to get the theta variation from there, and then after integrating both these equations using some kind of numerical method, you can get the solution for that problem. So in the next two classes, we are going to delve further into the ballistic equation. We are going to see if we can use this equation to get something about of the deceleration levels which are possible and the max deceleration level, because that's something which is important for the design of the spacecraft. And then also we are going to look at the temperature issues which are involved in returning back to Earth, because whenever you return back to Earth, heat is generated, and that is a big problem as far as spacecraft design is concerned. You don't have to only worry about the spacecraft going up, you also have to worry about the spacecraft going down. So I'll end this video now and I will see you in a lecture sometime soon. See you then.